So when you picture AI in your head, what do you see? Probably clean digital worlds, right? Maybe data centers, or self-driving cars on perfect roads, or algorithms just creating art. But what happens when you take an AI and throw it into one of the most chaotic, challenging, and frankly messy environments on Earth? Well, a new AI system is learning to do exactly that, to conquer the chaos of a metal foundry. Yeah, we're talking about the world of metal casting. Now, a lot of it has seen automation over the years, but it's still one of those places where humans do the absolute toughest jobs, and where a lot of our shiny advanced technology has really struggled to get a foothold. Okay, so just take a look at this workflow. You've got melting metal, making molds, pouring, cooling. A lot of this is automated now, but you can just see how many steps there are before we even get to a finished product. And it's in that final stage, that post-production part, where things get really, really tricky. You know, there's a reason they call it the 3D industry. It is dangerous, difficult, and dirty. And because of these brutal conditions, one of the most critical steps in the whole process has stayed surprisingly manual, simply counting the finished parts. That's right, a person actually has to stand there and physically count every single piece. Now, not only is this slow and super labor-intensive, but it's also incredibly prone to mistakes. We're looking at an error rate that can be anywhere from 3 to 15%. That creates a huge bottleneck in production and can cause all sorts of inventory nightmares. So you're probably thinking, why not just point a camera at the pile and let a computer do the counting? Well, it turns out that the seemingly simple task is an absolute nightmare for standard artificial intelligence. Let's break down exactly why. First off, the AI has to deal with a massive variety of product shapes and sizes. Then, you've got the fact that these parts are constantly overlapping, just piled on top of each other in a big jumble. The whole scene is also covered in sand and gunk left over from the casting process. And to top it all off, the factory might switch to a totally new product at a moment's notice, and the system needs to adapt instantly. No time for retraining. This image really gets to the heart of the problem. On the one side, you have an easy case, one clean object. A computer could probably handle that. But on the other side, well, that's reality. A chaotic pile of overlapping metal covered in sand. How is an AI supposed to make any sense of that mess? Well, this is the exact challenge that a new system, called DeepMachining, was built to solve. It is an AI designed from the ground up to thrive in exactly this kind of industrial chaos. And the key thing to understand here is that deep machining isn't just a single algorithm. It's a whole system. It uses a huge base of pre-trained knowledge, but, and this is the magic part, it can also rapidly adapt or fine-tune itself to the specific, messy conditions it's seen in real time on the factory floor. But how does it do that without getting totally confused or, forgetting what it's already learned? The secret is this really clever architecture. The easiest way to think about it is like an AI with two brains. So here's how it works. On one side, you've got the main branch. This is the seasoned expert. It's been pre-trained on tens of thousands of images, so it holds all the core knowledge about what castings generally look like. Its knowledge is basically locked in. Then, on the other side, you have the distillation branch. This is the fast-learning rookie. This part of the AI is totally trainable, and its whole job is to look at the current chaotic scene and quickly learn the specific features of the new part and all that environmental noise, like the sand and the debris. And here's what that looks like under the hood. You can see the main branch on the left. Its programming is frozen to protect all that expert knowledge. And then on the right, you've got the distillation branch, learning on the fly. The system then fuses the insights from both the expert and the rookie to make a final, super accurate decision. It's the best of both worlds. You get the stability of an expert with the adaptability of a rookie. Okay, so that all sounds great on paper, right? But how does it actually perform in a real-world test? The researchers decided to put deep machining up against several other state-of-the-art models to see who could really handle the heat of the foundry. And the result? Deep machining pulled off a staggering 97.8% average counting accuracy. And that's across 71 different products in a live, working foundry. That is just an incredible level of precision for such a messy environment. And it's not just that its average score is higher. Look at this chart. See how tight that little box is for deep machining? That means its performance is incredibly consistent, even on the hardest products. The other models, meanwhile, they really struggle. You can see their accuracy just plummets in the tougher cases because they just can't handle that level of complexity. But what does a 97.8% accuracy rate actually mean when you get it out of the lab and onto the factory floor? What's the real-world impact here? Well, the impact is huge. The miscount rate just plummeted from as high as 15% all the way down to below 3%. An entire hour of labor was saved per batch. That's a reduction of almost 14%. And the total cycle time for a batch of products was cut by a full hour. This isn't some small incremental improvement. It's a fundamental change to a major production bottleneck. Deep machining really proves that AI's potential isn't just limited to the clean, digital world. By designing systems that can actually adapt and learn in the face of real-world chaos, we are opening up a whole new frontier for automation. It really makes you wonder, what other 3D jobs, the dangerous, the difficult, and the dirty ones, are next on the list?